This talk is concerned with combinatorial search problems, problems that have the character of a puzzle. Just as the solver of a jigsaw puzzle is required to assemble the pieces so that they fit together perfectly, the solver of a combinatorial search problem is required to find a pattern or an arrangement for a finite set of objects so as to satisfy some set of constraints. A combinatorial search problem has the character of searching for a needle, the desired solution, in a very large haystack, the set of all possible solutions. Many combinatorial search problems have very simple and elegant solution algorithms, but there are others which require immense amount of computation, even though they've been studied extensively from the dawn of the computer age, or in some cases even for centuries. The basic question that we'll be examining in this talk is how to distinguish the easy combinatorial search problems from the hard ones, and in particular to determine whether the hard ones are really intrinsically hard or whether someday we may hope to crack them as well. Let me begin with a couple of examples to illustrate the kinds of problems we'll be discussing. The first example is called the shortest network problem, or the Steiner tree problem. It's a problem that might arise in the design of a local area telephone network. The data for the problem consists of a set of points in the plane. There are green points, which we are required to connect together, and red points, which are optional. The problem is to choose line segments, each of which joins two of the points, so as to interconnect all of the green points, possibly using some of the red points as intermediate junctions. So the rules of the game are that any pair of points may be joined by a line segment. And we want to find a collection of line segments of minimum total length that connect all of the green points together, possibly using some of the red points. Here is the optimal solution, or the minimal length solution, to this example. You'll notice that the solution is in the form of a tree, that all of the green points are connected together by the links of the tree, and that some of the red points are used as intermediate junctions, but others are omitted. The problem of finding an optimal solution to the Steiner tree problem has proved to be extremely elusive. There are examples with just a few dozen points which would tax the limits of even the most powerful computers. And yet, if we change the conditions of the problem ever so slightly, we obtain a problem which is essentially trivial to solve. If we consider the special case where there are no optional points, where all of the points are green, where all of the points are required to be connected together, then there is a very simple algorithm capable of obtaining minimum cost solutions to problems with tens of thousands of points. And this is a fundamental situation that arises constantly in the study of these combinatorial search problems, that even a very slight alteration in the conditions of a problem can make the difference between an intractable problem and a trivial one. As another example, let's consider a problem called the assignment problem, which involves matching workers with jobs. In this problem, we are given n workers and n jobs, and we want to find a one-to-one pairing or matching of the workers with the jobs at minimum cost. Each pairing of a worker with a job has associated with it a numerical cost. So the data for the problem consists of an n by n matrix where the rows correspond to the workers, the columns to the jobs, and the cells to the pairings. In this tiny 3 by 3 example, the first row would correspond to the first worker, the second row to the second worker, and so on. And similarly, the columns would correspond to the jobs. The entry 4 is the cost of pairing worker number 1 with job number 2. And in this particular example, the minimum cost pairing associates worker 1 with job 2, worker 2 with job 3, and worker 3 with job 1 for a total cost of 4 plus 1 plus 7, or 12. It turns out that although this problem seems to have the needle in the haystack character that's characteristic of hard combinatorial problems, it's actually a relatively easy problem. There's an elegant algorithm which allows us to solve very large instances of this problem, instances with thousands of workers and jobs, rapidly on a computer. So again, we see this phenomenon that some of these problems are remarkably easy, others remarkably resistant. With this background, let's take a stab at giving a general definition of the class of problems that we're interested in. We can define a combinatorial search problem in general as follows. Among a very large but finite structured set of possible solutions, find one that satisfies a set of stated constraints. There are some variants of this definition that are also of interest. Sometimes we're interested in decision problems, problems of a yes-no character, where we don't ask to find a solution, but simply to determine whether a solution exists. Sometimes, as in the example of the Steiner tree problem or the assignment problem, we're looking for an optimal solution. That is, we associate with every possible solution a cost, and we're seeking a solution of minimum cost. There are many areas of application arising in industry, in engineering, in management science, in the natural sciences, and in mathematics that give rise to these combinatorial search problems. Let me give a few examples. Scheduling is a rich and fertile area for such problems. So the scheduling of manufacturing operations, of airline flights, of classes within a school, scheduling the National Football League. All of these areas give rise to difficult combinatorial search problems. For example, in scheduling classes at a school, the data might consist of a list of the classes to be given, and for each an indication of which teachers are available for that class, which rooms are suitable, which hours of the day are suitable for the class. There might be constraints as to the number of classes a teacher can teach, constraints which say that 2 courses cannot be given at the same time because too many students want to take both, etc. And given all of these constraints, we want to weave together a schedule, put together the pieces of the puzzle in such a way as to satisfy the conditions. The various networks that girdle our society provide many interesting examples of combinatorial search problems. Here, the challenge is to route a commodity through a network so as best to use the capacity of the network. The commodities might be vehicles, as in a transportation network, phone calls, as in a telephone system, bits of information or packets of information, as in a computer network, oil or gas, as in pipeline systems. The field of VLSI design, the design of the microchips within our computers, is another important application area for combinatorial problems. The design of a very large-scale integrated circuit chip is analogous to the planning of a medium-sized city. Tens of thousands of components have to be placed on the chip, and wires interconnecting them appropriately have to be laid down on the chip subject to the technological and spatial constraints of the chip itself. So we get vast problems of arrangement and layout in this area. An area which is increasingly giving rise to interesting combinatorial search problems is computational biology. For example, in order to study the structure of a very large DNA molecule, it's necessary to break that molecule up into a large number of smaller overlapping fragments and to study the structure of each of these fragments, and then finally to mathematically reassemble the fragments by looking for pairs that are likely to overlap. And the number of arrangements here is very large, and we get a vast combinatorial problem. And similarly, in cryptography, the problem of breaking codes gives rise to important combinatorial problems with a number theoretic flavor. Many of the basic combinatorial search problems can be expressed in terms of structures called graphs. A graph is simply a set of points called vertices, certain pairs of which are joined by edges. So for example, here we have an edge joining these 2 vertices, an edge joining these 2, and so forth. Let me give you a couple of examples of combinatorial search problems involving graphs. A classic problem, which was first studied by the mathematician Euler in the 18th century, is the Eulerian walk problem. Given a graph, we ask, is there a closed walk that covers each edge exactly once? In other words, can you put your pencil down at a vertex of the graph and trace a chain of edges covering each edge exactly once and ending up back at the starting point? This seems like a difficult problem, but Euler discovered an elegant and simple criterion for its solution. Such a walk exists, assuming that the graph has no isolated vertices, if and only if the graph is connected, meaning that there's a path from any vertex to any other vertex, and each vertex has an even number of neighbors. Since these conditions are readily checked, the problem of deciding whether a graph has an Eulerian walk is an easy computational problem. Here's an example. We can easily see by inspection that this graph is connected, and each vertex indeed does have an even number of neighbors. For example, this vertex has 4 neighbors. And because these conditions are fulfilled, we don't have to bother to trace out the Eulerian walk. We know that the walk must exist. A very similar sounding problem is the Hamiltonian circuit problem. Here we're asking for a closed walk that starts at a vertex of a graph and visits all of the vertices of the graph, visiting each one exactly once. This problem, although it sounds deceptively similar to the earlier one, is much more difficult. In this example, we can begin searching. We can start at vertex 1 and successively visit vertices 3, 5, 2, 4, 9, 8, 7, 6, and 10, almost completing the tour, but failing because vertex 10, the last vertex on the walk, is not adjacent to vertex 1. It turns out that although there are many near misses possible in this example, there is no Hamiltonian circuit here. There is no closed walk that visits each vertex exactly once. As far as we know, the Hamiltonian circuit problem is a hard combinatorial problem. Every algorithm known for its solution runs into a combinatorial explosion, an exponential growth in the number of computation steps required to solve the problem as the number of vertices increases. And so this problem seems markedly more difficult than the rather trivial Eulerian walk problem. And this leads us to the central question that we'll be investigating here. Are these combinatorial explosions inevitable? Is the fact that we don't know how to solve the Hamiltonian circuit problem efficiently simply an artifact of our ignorance, or is there something inherent about the difficulty of this problem? In order to attack this problem as a legitimate mathematical question, we need some definitions. We need to make the definitions that draw the boundary between the tractable and the intractable problems, the easily solved problems and those that require a combinatorial explosion. The first person to really pose the appropriate definition was Jack Edmonds, a mathematician working around 1965. He suggested the following informal definition, that a problem is tractable if it can be solved in a number of steps bounded by a polynomial in the size of the input, that is, by some fixed power of the size of the input. So if the problem is of size n, then an algorithm that runs in time n squared or n cubed or n to the 5th power would make the problem tractable. But if the best we can do is, let's say, 2 to the nth power, exponential growth, which surpasses any polynomial degree of growth, then we would consider the problem intractable. And because of this definition, we can ask as a well-posed mathematical question, for example, is the Hamiltonian circuit problem intractable? Edmonds' definition has to be sharpened a little because it contains some undefined terms. What is meant by a problem? What does it mean to solve a problem? How do we count steps? What do we mean by the size of the input? Fortunately, these difficulties are easily overcome, and we can give a technical definition that corresponds to Edmonds' informal definition. To do so, we need a couple of conventions. The first convention concerns the format for the input. Different combinatorial search problems have inputs of different kinds. In some cases, the input is a graph. In other cases, a number or an array of numbers. In yet other cases, the input might be an algebraic formula or a string. But all of these forms of input can, in principle, be written down as strings of symbols and ultimately encoded as strings of zeros and ones. And so we adopt the convention that as a common format, we take the input to a problem to be a string of zeros and ones. And furthermore, we assume that any string of zeros and ones is a possible input, so there is no limit to the size of the input that might be presented to a problem. This also gives us a standard definition of size, because the size of the input is merely the length of the string of zeros and ones needed to encode it. We further make the convention that we'll work with decision problems, problems that have a yes-no answer. At first sight, this may seem restrictive because it excludes interesting problems such as combinatorial optimization problems. But there are very simple tricks by which you can take an optimization problem and derive from it a very closely related decision problem, such that obviously the decision problem is tractable if and only if the original optimization problem was. And so there is no real loss in restricting attention to decision problems. And so we're led to our first central definition. P is the set of all decision problems that are solvable in polynomial time. There's one more technicality. We have to talk about what we mean by an algorithm and the abstract model of a computer that we're going to use. But it turns out that there's wide latitude in this choice. We can stick with the best known model, which is the Turing machine, or with various other models that give rise to essentially the same theory. So we've now defined rigorously what we mean by the class of efficiently solvable decision problems, or polynomial time solvable decision problems. We can identify a problem with the set of accepted strings. And we can say then that a problem L, defined by its set of accepted input strings of zeros and ones, lies in the class P if there is an algorithm A which accepts the right strings, all those that should be accepted, that rejects all the strings that shouldn't be accepted, and runs in polynomial time. In other words, there is some polynomial, n squared, n cubed, whatever, such that on every string x, the running time of the algorithm is bounded by that polynomial evaluated at the length of x. In other words, the running time is bounded by some power of the length of the input. So now we have our definition of the class P, and we begin to study which combinatorial search problems or decision problems lie in P and which ones lie outside of the class. A fundamental definition which helps us bring order to the classification is the concept of polynomial-time reducibility. We introduce the notion of the reducibility of one problem L to another problem M. There are various intuitive interpretations that can be given to this definition of reducibility. One of them is that problem L is reducible to problem M if problem M is at least as hard as problem L, or if problem M is more general than problem L, so that problem L is a special case. Another interpretation is that problem L is reducible to problem M if a polynomial time algorithm for M would yield a polynomial time algorithm for problem L. Here's the technical definition. Decision problem L is reducible to decision problem M if there is a function f computable in polynomial time which essentially transforms the first problem to the second. In other words, f can take any input string presented to problem L, produce a corresponding output string f of x, which can be presented to problem M, and then the original string x will be accepted in L if and only if f of x is accepted in M. So this is the definition of reducibility of one combinatorial decision problem to another. And this notion of reducibility gives us a classification or a ranking of problems according to difficulty. Let's look at some of the properties of this notion of reducibility. We observe that if problem L is reducible to problem M, and problem M is solvable in polynomial time, then L is also solvable in polynomial time. And the diagram indicates how this is proved. Assuming that we have a box that will decide membership in M in polynomial time, then to solve problem L on an input x, we simply transform that input through the polynomial time transformation f to a new string f of x, and then present the new string to the decision procedure for M. The concatenation of these two operations, according to the definition, solves problem L. And so this is further confirmation that if problem L is reducible to problem M, then problem M is at least as hard as problem L. This means that we can gather evidence for the difficulty of some problem M by showing that many seemingly hard problems are reducible to it. Let me give you a concrete example of reducibility between two combinatorial problems. In this example, one of the problems is the so-called satisfiability problem that arises in propositional logic, or computer scientists might say Boolean algebra. And the second problem involved is a problem arising in graph theory called the three-coloring problem. Let's first deal with the satisfiability problem. The satisfiability problem involves expressions that are built up by applying the logical connectives, and, or, and not, to propositional or Boolean variables. So we start with propositional variables, A, B, C, etc., each of which may be assigned the value true or the value false. A literal is either a propositional variable or its negation. So a bar denotes the negation of variable a. A bar is true precisely if a is false. Next, we define a clause as the logical OR of a set of literals. So the clause shown here will be true if either a is true, or b is false, or d is false, so that d bar is true, or f is true. And finally, we define a conjunctive normal form formula as the AND, or the logical AND, of a set of clauses. So the formula shown here will be true if each of the clauses is true, and any given clause will be true if at least one of the literals in that clause is true. We'll say then that a conjunctive normal form, or CNF formula, is satisfiable if there is some assignment of the truth values to the variables that makes the formula true. The formula shown here is satisfiable because we can make it true by setting B, C, and D false and A true. If we do that, then the first clause is true because A is true. The second and third clauses because B is false, hence B bar is true. And the last clause because D is false, so that D bar is true. Each of these clauses contains a true literal, and hence each is true and their conjunction is also true. The satisfiability problem then takes as its input a CNF formula, and the output is the input is accepted if that formula is satisfiable. Now let's turn to the second problem that's involved in our reduction. This is a problem from graph theory called the three-coloring problem. A graph is said to be three-colorable if we can color each of its vertices with one of the three colors, red, green, and blue, in such a way that no two adjacent vertices are assigned the same color. It turns out that this graph isn't three-colorable. We can trace through a chain of reasoning that will determine this. First of all, because vertices 2, 3, and 4 form a triangle, no two of them can get the same color, so they must get distinct colors. Similarly, 3, 4, and 6 form a triangle, so they must get distinct colors. And since only 3 colors are available, 2 and 6 must get the same color. And continuing a chain of reasoning along those lines, we will eventually conclude that there is no assignment of colors such that we avoid having two adjacent vertices get the same color. So the decision problem here is the three-coloring problem, given a graph to decide whether or not it can be colored with 3 colors. Now we're going to link these two problems by showing that the three-coloring problem is reducible to the satisfiability problem. If you recall the definition, this means that we have to give a transformation which is easily computed, that is, polynomial-time computable, which will take any instance of the three-coloring problem, that is, any graph, and produce from it an instance of the satisfiability problem, that is, a conjunctive normal form formula, such that the graph is three-colorable if and only if the formula that we've produced is satisfiable. In this particular case, what we have to do is define appropriate propositional variables to describe all of the conditions that are required of a three-coloring. And so we'll do that in the following way. For each vertex I in the graph, we'll introduce a variable r sub I, which is true if vertex I gets the color red, b sub I, which is true if vertex I gets the color blue, and g sub I, which is true if and only if vertex I is assigned the color green. And in terms of these Boolean or propositional variables, we can write down all the conditions of the problem. Each of the conditions will be expressed as a clause. So first of all, for each vertex I, we write down the clause r sub I or b sub I or g sub I. That simply says that vertex I must receive some color. It's either red or blue or green. The next trio of clauses associated with a given vertex I assert that the vertex doesn't receive two distinct colors. For example, the clause not r sub I or not b sub I asserts that either the ith vertex does not receive the color red or it does not receive the color blue. In other words, it's not both red and blue. And similarly, the next two clauses assert that it's not both red and green, and that it's not both blue and green. The other clauses that we have to write express the condition that two adjacent vertices must not get the same color. So we look at each edge of the graph, ij, and we write three clauses for that edge. The first one, not r sub I or not r sub j, says that either I is not red or j is not red. In other words, I and j don't both get colored red. That would be a violation of the coloring conditions. And the other clauses similarly say that the two adjacent vertices I and j are not both blue and are not both green. And we see that the totality of these clauses expresses all of the conditions that are required of a coloring. So that this set of clauses comprising a CNF formula is satisfiable if and only if the original graph could be colored with three colors. And furthermore, it's rather obvious that the algorithm to go from the graph to the set of clauses is rather trivial and thus can be carried out in polynomial time. So this establishes that three coloring is reducible to satisfiability, or in other words, that satisfiability is at least as general or at least as hard a problem as three coloring. Now we need one more key definition before we can approach the main results of our theory. It turns out that most of the combinatorial problems that arise in applications have a characteristic form which is captured by the definition of a class of problems called NP. These problems have the character that they are asking for the existence of a structure which may be hard to find, but once pointed out is easy to check. For example, in the case of the Hamiltonian circuit problem, we're asking for a closed walk in a given graph that visits each vertex exactly once. It may be extremely difficult to find such a walk, but if somebody gives you one, gives you the list of successive vertices along such a walk, it would be very trivial to check that list against the graph and to verify that it really was a closed walk visiting every vertex of the graph. So in that sense, the Hamiltonian circuit problem is easy to check. Let me give a more precise definition of the class of problems NP. We'll say that decision problem L lies in NP if and only if there exists a polynomial time decision algorithm A with two inputs, x and y, such that the input x should be accepted in problem L if and only if there is another string y that we call the witness or the solution of length bounded by a polynomial in the length of x, such that algorithm A accepts the pair x, y. So the idea behind this definition is that even though problem L might be hard, it lies in NP if once a solution is handed to you, it's not too difficult to check the solution against the input and verify that it is indeed a solution. To illustrate this definition, let's talk about the following decision problem. Given an integer, to decide if the integer is composite or factorable. A composite integer is a number like 15, 3 times 5, or 56, 7 times 8, which can be written as the product of two factors, as distinguished from prime numbers like 7, 11, or 13, which cannot be factored in such a way. Now, how do we see that the set of integers that can be factored, the set of composite integers, lies in the class NP? Well, if an integer can be factored, then there's an obvious witness to that fact, namely one of the factors. And the decision problem of checking the factor against the number is trivial. So for example, if we were presented with the number 56 as an input, then an appropriate witness to the compositeness or factorability of 56 would be one of its divisors, 14. And given that witness, we would simply check that 14 divided into 56 and was neither equal to 1 nor equal to 56. So even though we don't know that the problem of testing whether a number is composite lies in P, it is immediately seen that it lies in this broader class NP. And the reason for the interest in NP is that nearly all of the combinatorial problems typically arising in practice have versions that lie within the class NP. So for example, the Eulerian walk problem lies in NP because the witness in this case would be just the walk itself, and it's easy to check the walk. And for similar reasons, the Hamiltonian circuit problem, the satisfiability problem, and the 3-coloring problem all lie in NP. For example, in the case of the 3-coloring problem, the witness would be simply the assignment of colors. And given that assignment, it's rather trivial to check that no two adjacent vertices have the same color. It's also interesting, as a side comment, that sometimes the negations or the complements of these properties are not so obviously in NP. For example, if we look at the Hamiltonian circuit problem, there's an obvious witness to the existence of a Hamiltonian circuit, namely the circuit itself, but there's no obvious witness to the non-existence. In other words, there's no short hint or witness that one could write down which you could hand to somebody and thus enable that person to easily verify that a given graph didn't have a Hamiltonian circuit, or at least we don't know of any general way of providing such a witness. So then what is the relationship between the class P of problems that are easily solved, problems that are solvable in polynomial time, and NP, the class of problems for which witnesses are checkable in polynomial time? It's easy to see that every problem in P lies in NP, but what about the converse? Does every problem in NP lie in P? Is P equal to NP? This is generally considered the single most important open problem in theoretical computer science. Let's look at some of the consequences of the unlikely proposition that P is equal to NP. If P were equal to NP, then we could say that finding a solution to a problem is no harder than checking a solution, because after all, P is the class of problems for which solutions are easy to find, and NP is the class for which solutions are easy to check. Putting it in terms of mathematical proof, it would say that finding a proof of a theorem is no harder than checking a proof, something that we are hardly inclined to believe if we think back to our tussle with plane geometry in high school, where finding proofs was sometimes difficult, but we knew that checking a proof was a simple matter of determining that each line of the proof followed from the axioms and postulates. If P were equal to NP, it would further mean that many seemingly intractable problems, some like the problem of factoring integers, which have remained intractable even through the centuries, would turn out to be solvable in polynomial time. In short, if P is equal to NP, then combinatorial explosions would be tamed. And so we hardly dare to believe that P is equal to NP, and yet we have no decisive proof as yet that P is unequal to NP. However, some progress can be made. And the key to this progress is the definition of an NP-complete problem. The NP-complete problems are, in some sense, the hardest problems within the class NP. In other words, the hardest combinatorial decision problems typically encountered in practice. A decision problem L is said to be NP-complete if, first of all, it lies in the class NP, and secondly, L is such a general problem that every problem in NP is reducible to L. Every problem in NP can be converted or re-encoded or transformed to the problem L. So the NP-complete problems are the richest or most general or most universal problems in the class, and hence the most likely candidates to be the hardest problems in the class. We can immediately draw the following inference, that if a problem L is NP-complete, then L lies in the class P if and only if P is equal to NP. If L lies in P, for example, then because every problem in NP is reducible to L, every problem in NP would be in P also by virtue of that reducibility, and hence P would be contained in NP. And so it's the status of the NP-complete problems which is of particular interest in studying the question of equality between P and NP. In 1971, Stephen Cook proved a fundamental theorem. He showed that the satisfiability problem is NP-complete. In other words, every problem in NP is reducible to satisfiability. If we had a polynomial time algorithm for satisfiability, it would be a panacea. It would allow us to solve every problem in NP in polynomial time. Another way to look at this is that propositional logic, or Boolean algebra, is rich enough to allow an enormous variety of combinatorial problems to be expressed within that format. Following upon the heels of Cook's result, I showed in 1972 that the majority of the common elusive combinatorial search problems such as Hamiltonian circuit, three-coloring, Steiner tree, and many others are NP-complete. So the phenomenon of NP-completeness is not restricted to satisfiability, but is typically enjoyed by most of the hard problems that arise in practice. Most of the hard problems turn out to be NP-complete and hence unlikely to be solved in polynomial time, because if they were, then P would be equal to NP. Solving would be no more difficult than checking. Interestingly, it turned out that there was a school of researchers in the Soviet Union who were independently pursuing these problems. And Leonid Levin, who is now a professor at Boston University, in 1973 independently proved similar results, except that his universal problem, instead of satisfiability, was a problem similar to jigsaw puzzles, which involved arranging a set of dominoes to cover a finite region of the plane subject to constraints about how dominoes could be fitted together. So what is the moral of the story? We now have this enormous list of NP-complete problems. By now, thousands of such problems are known. If a problem is NP-complete, then we cannot expect to find a fast algorithm to solve it in all cases, because if we could, then that algorithm would be a universal method of getting polynomial time solutions to all manner of combinatorial problems, in particular all the problems in NP. So the NP-completeness of a problem in practice is an indication that we can't expect to solve it with a polynomial time algorithm. We have to lower our sights and instead look for algorithms that handle most instances. Such an approach leads us to notions of the probabilistic analysis of algorithms, where we try to quantify the concept of handling most instances. Another approach that we can use to cope with NP-complete problems in the case of optimization problems is to look for algorithms that, although they don't give solutions of minimal cost, give solutions of near minimal cost, near optimal solutions. And so for the past couple of decades, since the phenomenon of NP-completeness became well known, people have been using approaches such as these to try to cope in practice with these elusive and possibly inherently intractable combinatorial problems. But to tell you about all of those approaches would be another story, and we'll save that for another day. Thank you.